capital E is finite cyclic extension of F of degree n. G of E over F is cyclic group and order of G of E over F is equals to n. So order of G of E over F is equals to n. Second condition. So E is splitting field of irreducible polynomial x power n minus b belongs to f of x. So this is theorem statement 17.3.8. So proof. So our assumption, first condition is true. The first condition is true. So E is finite cyclic extension degree n over f. So first condition is true. We have to show that second condition. E is splitting field of irreducible polynomial x power n minus b belongs to f. So E is equals to f of x, f of x, f of alpha, where alpha is root of x power n minus b. So this is. So assume first condition. So suppose E is finite cyclic extension of f. So E is finite cyclic extension of f of degree n. So this is first condition. So we have to show that using first condition, we have to show that second condition. Okay. So second condition. Suppose E is finite cyclic extension of f of degree n. So that is, so degree of E over f. So degree of E over f is n. Degree of E over f is n is given in question. So degree of E over f is equals to n. So this can be written as, so degree of G of E over f. So degree of G of E over f, that is G of E over f is cyclic group of order n. So is given condition. So this is up to first statement. Suppose E is finite cyclic extension of f of degree n. So that is order of E of E over f is n, that is equals to order of G of E over f. So that is, so this can be represents order of G of E over f is a cyclic group of order n. So let gamma be the generator of G of E over f. So this is cyclic group is nothing but, so then there exists at least one generator. Every cyclic group has at least one generator. So we are taking a generator for G of E over f. So sigma will be the generator of G of E over f. So this is cyclic group. So we are taking one generator. So sigma be the generator of G of E over f. By the Hilbert lemma, then there exists alpha belongs to E star such that, so sigma is equals to omega is equals to sigma of alpha into alpha inverse. So by using Hilbert lemma, omega is equals to sigma of alpha into alpha inverse. So that is sigma alpha is equals to, so omega into alpha. So sigma alpha is equals to omega into alpha. Also, so sigma dash of alpha is equals to omega into alpha. So next, so this is nothing but sigma power 1 of alpha is equals to omega into alpha. So sigma square of alpha. So sigma square alpha can be written as sigma alpha. So sigma square alpha can be written as sigma alpha. So but sigma alpha is equals to omega into alpha. So substitute here. So sigma omega into alpha. So next, so this is of the form. So this one. So sigma of alpha is equals to omega into alpha. So again apply this one. So sigma of alpha. So omega into, in place of alpha, omega alpha is there. Omega into omega alpha. So sigma square alpha is equals to omega square alpha. So next, continue this process. Sigma power I alpha is equals to omega power I into alpha for all I. So this is equation number 1. So because, so sigma is generator of G of E over F. So generator is nothing but, so sigma square, sigma cube, sigma power 4. In each and every case, so it generates all the elements in a G of E over F. Okay, so it generates each and every element in a group. Cyclic group is nothing but a generator which can generate each and every element in a group. So sigma power 1, sigma square, sigma power 3, sigma power 4, so which all generates the elements of G of E over F. Next, consider sigma power I of alpha power n. Sigma power I of alpha power n is equals to sigma power I alpha whole power n. So sigma power I alpha is equals to, from equation number 1, so by equation number 1, so omega power I into alpha whole power n. So omega power I whole power n into alpha power n. So that is nothing but omega power n into whole power I into alpha power n. So but omega is a primitive nth root of unity. So but omega is primitive nth root of unity. So here, so you can see, so omega is the primitive nth root of unity. So therefore omega power n is equals to 1. So this is primitive nth root of unity. So then omega power is equals to 1. So substitute omega power n is equals to 1 on here. So we are getting sigma power I of alpha power n is equals to, so this is 1, so remaining alpha power n. So that is sigma power I of alpha power n is equals to alpha power n for all sigma I belongs to G of E over F. So therefore alpha power n belongs to F. So which is shows that, so sigma is generator and alpha 1, alpha 2 up to alpha n. So alpha 1, alpha 2 up to alpha n. So these all are elements belongs to F. So alpha power n also belongs to F, and alpha power n belongs to G of E over F. By the definition of fixed field, EH E of EH is equals to capital F. So these two are equal by using definition of fixed field definition. So these two are equal. E of G of E over F is equals to F. Alpha power n is belongs to F. Next, so B is equals to alpha power n. So we are taking some root. So B is equals to alpha power n, then is given x power n minus B belongs to F of alpha. So since omega power I into alpha power n is equals to omega power n whole power I into alpha power n. So omega power n is equals to 1 because primitive nth root of unity. So that is alpha power n. Alpha power n is equals to beta. Alpha power n is equals to b. So here alpha power n is equals to b. So then omega power I into alpha whole power n minus b is equals to 0. So this is nothing but, so this is shows that x power n minus b belongs to f of x. So in place of x here, omega power I into alpha, which shows that omega power I into alpha is a root of x power n minus b. So omega power I into alpha is a root of given equation x power n minus b for I is equals to 1 to infinite. So that is x power n minus b is equals to summation I is equals to 1 to n x minus omega power I minus alpha, x minus omega power I minus alpha. So next, so we have to show that x power n minus 1, x power n minus b is irreducible polynomial over f. So this is irreducible polynomial over f. So irreducible polynomial over f. So let x power n minus b belongs to f of x into g of x. A polynomial is said to be irreducible. So it can be written as product of two polynomials, f of x into g of x. So where f of x is non-constant polynomial, so irreducible monic polynomial. If f of x is non-constant polynomial, is nothing but f of x has degree at least 1. So degree at least 1. So we can say that f of x is non-constant polynomial. So where f of x is non-constant irreducible monic polynomial. If omega power I into alpha is one of the root of f of x, then for each positive integer say j, so such that sigma power j minus I of omega power I into alpha is equals to sigma power j minus I into omega power I into sigma power j minus 1 of alpha. So this is equation number 1. So this can be written as, so splitting sigma power of sigma of omega sigma of alpha. Sigma of omega power I into alpha is equals to sigma of omega power I into sigma of alpha. This is equation number 1. Since omega belongs to f, that implies omega I also belongs to f. So that implies sigma power j minus I of omega power I is equals to omega power I. So ఇది already prove చేసాం ఇక్కడ starting లో. So we can also write sigma power j minus I alpha is equals to sigma power j minus I into alpha. These two conditions are here. Equation 1. So this is equation 1. So sigma power I into alpha is equals to omega power I into alpha, and also, so this is condition 2. Sigma power I of alpha power n is equals to alpha power n. So substitute equation 2, we are getting, so these two values. So these two values substitute in equation number 2. So we are getting sigma power j minus I of omega power I alpha is equals to omega power j minus I into alpha is equals to omega power j into alpha. Since omega power j minus 1 is belongs to g of e over f, so we get omega power j into alpha is equals to sigma power j minus 1 omega power I into alpha is also root of f of x. So clearly, we can bring this on this side. Some elements are cancelled. So after, we are getting sigma power j minus 1 of omega power I into alpha is equals to omega power j minus alpha, which shows that, so this is also a root of f of x is nothing but x power n minus b. So all the roots of omega power I into alpha of x power n minus b are the roots of f of x. So all the roots of x power n minus b, each and every root of x power n minus b are the roots of f of x. So therefore x power n minus b is equals to f of x into c. So where c is content of the where c is constant, so that is c is equals to g of x. So is nothing but x power n minus 1 can be expressed as f of x into g of x in these two polynomials. So one of the polynomial is constant. So one of the polynomial is constant is nothing but, so given x power n minus 1 is irreducible polynomial. So irreducible is nothing but a polynomial f can be written as f of x into g of x. A polynomial f of x is can be written as product of two polynomials. In these two polynomials, at least one of the polynomial is constant polynomial. At least one of the polynomial is constant polynomial. Then we can say that f of x is irreducible polynomial over q. Okay. So here x power n minus 1, x power n minus b can be written as f of x into g of x. So here f of x is non-constant polynomial. Is given also f of x is non-constant polynomial. So remaining x power n minus 1b can be written as f of x into c. So where c is nothing but g of x. C is nothing but g of x is nothing but c. G of x is constant polynomial. In these two products, g of x is constant polynomial. Therefore, x power n minus b is irreducible polynomial by using the definition of irreducible. Since the roots alpha comma omega power 1 into alpha omega square into alpha up to omega power n minus 1 into alpha of x power n minus b belongs to E. So we have E is equals to, so all roots, E is equals to f of all roots of x minus n minus b, x power n minus b, alpha comma omega into alpha comma omega square into alpha up to omega power n minus 1 into alpha. So this is nothing but all roots is equals to alpha. E is equals to f of alpha. So therefore E is splitting field of x power n minus b over f. So this is first condition. The first condition. So E is finite cyclic extension of degree n over f. So we have to show that E is splitting field. E is splitting field of irreducible polynomial. So here E is splitting field and Pujaism, and also we have to show that E is irreducible polynomial. So x power n minus 1 is equals to f of x into g of x. In these two functions, g of x is constant polynomial. So therefore x power n minus 1 is x power n minus b is irreducible. So splitting field and irreducible, two conditions. And also further E is equals to f of alpha, where alpha is root of x power n minus b. Alpha is root is nothing but all roots, alpha comma this one. So alpha is root, all roots of x power n minus b, alpha comma omega into alpha, omega square into alpha, omega power n minus 1 into alpha. E is equals to f of alpha is splitting field of x power n minus b over f. So this is first condition to second condition. First condition, our assumption first condition is true. We have to show that second condition. So splitting field and irreducible polynomial and E is equals to f of alpha, where alpha is a root of x power n minus b. So three conditions. So next our assumption. So second condition is true. The second condition is true is nothing but E is a splitting field of an irreducible polynomial x power n minus b belongs to f of x. Further, E is equals to f of alpha, where alpha is root of x power n minus b. Now we have to prove that E is a finite cyclic extension of degree n over f. E is finite cyclic extension of degree n over f is nothing but, so the E is cyclic extension. So cyclic extension is nothing but, then there exists a cyclic group. So second condition to first condition. Let C belongs to E with a root of x power n minus b belongs to f of x. And so b is equals to c power n. So c be the root is nothing but, substitute c on here. C power n minus b is equals to 0. B is equals to c power n. B is equals to c power n. Then c comma c omega comma c omega square up to c into omega power n minus 1 are n distinct roots of x power n minus b, where omega belongs to f is a primitive nth root of unity. Omega is the primitive nth root of unity. And x power n minus b is separable and irreducible polynomial by condition number 2. So this is separable extension and irreducible polynomial. E is equals to f of c is a separable extension of f, where c is a root of x power n minus b. For each sigma belongs to g of E over f, define a function gamma, define a function psi g of E over f to a subset to z by generator of n. So is defined by psi of sigma is equals to k belongs to z, such that sigma of c is equals to omega power k into c. So psi of omega is equals to k belongs to z, such that sigma of c is equals to omega power k into c. So this is nothing but total, our assumption k bar. This total is k bar. Psi of sigma is equals to k bar. So we are taking sigma 1 comma sigma 2 belongs to g of E over f, such that So sigma 1 of C is equals to omega power k into C. So sigma 2 of C is equals to omega power j into C. So sigma 1 into sigma 2 of C. Sigma 1 of sigma 2 of C. Sigma 1 of sigma power j into C. So omega power k into omega power j into C. So we define this function. We have to show that the defined function is homomorphism. So we have to show that the defined function is homomorphism. Homomorphism conditions phi of A into B is equals to phi of A into phi of B. So this is first condition of homomorphism. So this is homomorphism condition. So we define a function psi is defined as psi of omega is equals to, so sigma of C is equals to omega power k into C. So now we have to show that the given defined function psi is homomorphism. So we are taking sigma 1 into sigma 2 belongs to G of E over F. So sigma 1 of C is equals to omega power k into C. So sigma 2 of C is equals to omega power j into C. And sigma 1 into sigma 2 of C is equals to, so sigma 1 into sigma 2 of C, sigma 1 into omega power j into C, and omega power k into omega power j into C. So sigma 1 into sigma 2 of C is equals to omega power j plus k into C. So psi of omega 1 into omega 2 is equals to I comma j belongs to z, I comma j, I plus j belongs to z, such that sigma 1 into sigma 2 of C is equals to omega power k plus j into C. So this is nothing but k plus j whole bar. So this can be using this condition, our defined function. So omega power k. So the total function can be written as k bar. Here omega power k plus 1. Omega power k plus 1. So psi of omega 1 into omega 2 is equals to k plus j whole bar. K plus j whole bar. So this can be written as k bar plus j bar. So but k bar is equals to psi of omega is psi of omega 1 plus j bar is equals to psi of omega 2. So therefore psi is homomorphism. Is clear? So this is homomorphism condition. Psi of omega 1 into omega 2 is equals to psi of omega plus psi of omega 2. So psi is homomorphism. Also psi is bijective. So that psi is isomorphism. So bijective is nothing but, so it is 119 onto conditions. So psi satisfies 1 condition, onto condition, and homomorphism. So then psi is isomorphism. So psi is isomorphism. So now degree of f of c over f is equals to degree of the minimal polynomial of f. So degree of the polynomial is nothing but x power n minus b. So x power n minus b polynomial degree is n. That is equals to degree of x power n minus b. So therefore f of c, degree of f of c over f is equals to n. Since e is equals to f of c, e is equals to f of c is a finite separable and normal extension of f. So this is e is equals to f of c is finite separable and normal extension of f. So therefore we have e is Galois extension. So we know that every finite separable extension is Galois extension. Every finite separable normal extension. Every finite separable normal extension is Galois extension. So therefore E is Galois extension of f. So order of G of E over f is equals to degree of E over f. So degree of E over f can be written as f of c. E is equals to f of c. This E is equals to f of c over f is equals to n. Since psi function g of E over f to a subset to z by n is isomorphism, because psi is unknown function, onto function, it satisfies homomorphism condition also. So this is isomorphism. So G of E over F is isomorphic to a subgroup of Z by N. A subgroup of Z by N. So G of E over F is isomorphic to cyclic group. So this is Z by generator of N. It shows that, so this is a cyclic group. So G of E over F is isomorphic to a cyclic group. So therefore, G of E over F also a cyclic group. Here, Z by generator of is cyclic and a subgroup of Z by generator of N is cyclic. So this is cyclic group. Z by generator of N is a cyclic group. Every cyclic extension of F of degree N. So this is first condition. Once again, theorem statement. If let F contains primitive nth root of omega of unity, then the following are equivalent. So first condition is finite cyclic extension of degree n over F. A splitting field of an irreducible polynomial x power n minus b belongs to f of x. Further, E is equals to f of alpha, where alpha is the root of x power n minus b. So this is the theorem statement. So 17.3.8 theorem. 17.3.8 insolvable groups. Polynomials by radicals. Polynomials solvable by radicals. So definition, a field extension K of a field F is said to be a radical extension of F if there exists a sequence of fields F is equals to F0 subset R is equals to F1, if subset R is equals to F2, up to subset R is equals to FR is equals to K, such that I is equals to 1 to R, Fi is equals to Fi minus 1 of omega I, where omega I is belongs to f of I with the property omega power I power n is belongs to Fi minus 1 for some Ri greater than or is equals to 1. So this is the definition of polynomials by solvable by radicals. So this is 7.7 17th chapter. So 13.3.17. So Gauss theorem. So this is very important theorem. So Gauss theorem. Let f of x belongs to z of x be a primitive polynomial, then f of x is irreducible over q if and only if f of x is reducible over z. So f of x is reducible over q, then we have to show that the same f of x is reducible over z. So here f of x is primitive polynomial. F of x is primitive polynomial. Proof. If f of x is reducible over z, clearly f of x is reducible over q. So suppose that f of x is reducible over q, we can write f of x can be written as product of two polynomials. F of x is equals to g of x into h of x. So where g of x and h of x are the constant polynomials. So we can write so g of x is equals to some constant a by b into g1 of x, where so g1 of x belongs to z, it is primitive, and h of x also can be written as c by d. H of x also can be written as c by d into h1 of x. So here g1 comma h1. So g1 comma h1 are the primitive polynomials. So g is equals to some constant into g1 of x where g1 of x is primitive polynomial, h is equal to some constant into h1 of x, where h1 is primitive polynomial, and a comma b comma c comma d. So all our constants belongs to z. And so f of x is equals to a into c. So f of x into g of x is equals to a into c, g1 of x into h1 of x. So we can multiply f of x into g of x. So that is equals to a into c, g1 of x into h1 of x. So comparing the constants, we get ab is equals to ac is equals to bd. So compare coefficients, ac is equals to bd, since f of x sine, g of x sine, g1 of x sine, h1 of x. So the product are primitive. These all polynomials are primitive polynomials. So therefore, f of x is equals to g1 of x into h1 of x. So remaining all are constants. So f of x is equals to g1 of x into h1 of x. So but our assumption, g1 and h1 is primitive polynomials. So g1 and h1 is primitive polynomial. So degree of g1 of x is equals to degree of g of x is greater than 0, and similarly degree of h1 of x is equals to degree of h of x is greater than or greater than 0, hence f of x is reducible polynomial. So theorem statement, f of x is reducible over q, so the same polynomial is reducible over z. So but f of x is primitive polynomial. So f of x is primitive polynomial, f of x is reducible over q, if and only if f of x is reducible over z. So this is important for short question. Next, separable and normal extensions. So definition. So definitions. An irreducible polynomial f of x belongs to f of x is called separable polynomial if and only it has its roots as distinct. Is nothing but f of x polynomial is said to be a separable polynomial. It has distinct roots. So clearly, every first degree polynomial is separable polynomial. So because every first degree polynomial has distinct roots. Clear? Is nothing but x has only single root. So every first degree polynomial is separable. So definition, an irreducible polynomial f of x belongs to f of x is called a separable polynomial if all of its roots are distinct. Is nothing but a polynomial is said to be separable, all roots are distinct. So next, second definition, a polynomial f of x belongs to f of x is called separable if all of its irreducible factors are separable. All of its irreducible factors are separable. So if alpha belongs to E, then x minus alpha belongs to M is separable for M greater than or is equals to 1. So this is irreducible factor. Next definition. Suppose f subset R is equals to E and alpha belongs to E is said to be a separable over F if alpha is algebraic over F and the minimal polynomial satisfied by alpha is separable. So these are the definition. And also a field F is called perfect field if each of its algebraic extensions are separable. Next, normal extension definition. In algebraic extension, K of F is said to be a normal extension of F if each of irreducible polynomial f of x over f having a root k split into linear factors over k. So it can be split into a linear factors over k. So in this example, in this normal extensions, every finite extension of a field of characteristics is zero is simple extension. So if characteristics is zero, then we can say that, so this is simple extension. So next class, for this theorem, every finite separable extension of a field f is a simple extension of f. Is nothing but every finite separable extension is simple extension. So next class theorem. So this is also important for long question. Every finite separable extension is simple extension. So here, a non-constant polynomial f of x over f is said to be solvable by radicals if its splitting field L of f of x over f is contained in radical extension of f. So for example, so we can say example, f of x is equals to x square plus ax plus b be a monic quadratic polynomial over q. So monic polynomial is nothing but leading coefficient is 1. So x square plus ax plus b, highest polynomial is highest degree is 2. So x square leading coefficient is 1. So then we can say that f of x is monic polynomial. The roots of f of x, so minus b plus or minus, so using formula minus b plus or minus square root of b square minus 4ac by 2a. So here in place of b, a is there, in place of c, b is there. Alpha 1 is equals to minus a plus square root of a square minus bc 4b by 2. Alpha 2 is equals to minus b minus root of a square minus 4b by 2. So we write L is equals to q of omega, where omega is equals to root a square minus 4b. And also omega square also belongs to q. So here omega is same, root of a square minus 4b, a square minus 4b. L can be written as L is equals to q of omega, where omega is equals to root a square minus 4b. So similarly, omega square also belongs to q. So that L is a radical extension of q. So also L is itself splitting field of f of x over q. So this is radical extension, L is radical extension, and L is splitting field of f of x over q. Hence, f of x is solvable by radicals. Okay. So this is radical extension and splitting field. So we can say that f of x is solvable by radicals. A group G is solvable if and only if G power n. So G power n is equals to E for some n greater than or is equals to 1. A group G is solvable. So condition is G power n. So G power n is equals to E. E is nothing but identity element in a group G. So n is equals to n greater than or is equals to n is nothing but n is equals to 1, 2, 3. N is greater than or is equals to 1. So proof, if G power n is equals to E, so G1 subset R is equals to G2, subset R is equals to G3 up to G power n is equals to E is normal series, and so G power I by G power I plus 1 is abelian. So g power I by g power I plus 1 is abelian, hence g is solvable. Every normal extension has abelian factors. Every normal series has abelian factors. So gi by gi plus 1 is abelian, hence g is solvable group. So conversely, if g is solvable, then there exists a normal series. So normal series g is equals to E with abelian factors. Every normal series has abelian factors. So then gi plus 1 is subset R is equals to gi dash for I is equals to 1 to infinite. So using induction, we get gi subset R is equals to gi for all I. Hence g power k plus 1 is equals to I. So this is nothing but every group G is solvable if and only if g power n is equals to E. So if G is solvable, then there exist a normal factors, normal series. If G is solvable, then there exists a normal series, and the normal series has abelian factors. The normal series has abelian factors. So therefore, G is solvable. So sufficient condition. So G is solvable. G is solvable. G power n is equals to E. So then there exists a normal series with abelian factors. So we know that every normal series and abelian factors as solvable. So therefore, G is solvable group. So this is a theorem. So we will see in next class.